because it was just the original, the definition of Riemann zeta.
Okay. Should I start?
Hang on.
Okay.
Go ahead, Yashovardhan. So sorry.
Okay. So should I start?
Yes. Hang on. Go ahead. Please start.
Okay, sir. Riemann in his famous paper in 1859, he defined a complex function as the infinite sum of this 1 upon n to the power s, and he denoted this function as zeta, and for the complex variable of s. This is valid for real part of s is greater than 1. He also proved that this zeta function is analytic continued to the whole complex plane except for s is equal to 1. And we have a pole at simple pole at s is equal to 1 with residue 1. And if we see in the left hand side, we have zeta function, gamma function, and this pi. And if we know zeta function for the right half plane, so from the left hand side, we will able to calculate the zeta function for the left half plane. To move further to see further properties and special values of this Riemann zeta function, we have to move 100 years before to the Euler. So Euler have studied the same function with a real variable. So he proved in 1735 that zeta of 2m is nothing but this in the right hand side that we have. So if you look, if you observe this, so except for pi to the power 2m, everything is rational. So we can say that zeta functions, Riemann zeta functions, at even integers, positive even integers, behave as pi to the power 2m multiple of a rational number. So we can say they are transcendental. Now, one should ask question, a natural question, what we can say about odd positive integers or odd integers. So it is believed that every of zeta 3, zeta 5, all of them are transcendental. It is known as a conjecture, but we do not have any proof to this. Euler have proved this theorem, zeta of 2m transcendental, that they are transcendental in 1735. After him, nearly more than 200 years, we do not have any upgrade regarding this, whether zeta 3, zeta 5, or any of them are irrational or rational or transcendental or anything. So then a mathematician, a French mathematician comes, and his name is Roger Apri. So he proved that zeta 3 is an irrational number. And this proof was so peak and so career defining for him that it is written in his gravestone that zeta 3, that is 1 plus 1 by 8 plus 1 by 27, cannot be written as a fraction of integers. Now, what is new? After him, we have some new results in the same direction. So in 2001, these authors have proved that there exist infinitely many zeta values, zeta of 2m plus 1, which are irrationals. But we cannot say whether all of them are irrationals or not, or specific which one of them are irrational. The next result is due to Zudlin, and he said that at least one of them, 4, I mean, if with the fours are the zeta 5, zeta 7, zeta 9, or zeta 11, at least one of them will be irrational. But still, explicitly, we cannot say whether zeta 5 or zeta 7 or any one of which one of them is irrational. So still, after Roger Apri's proof, we do not have anything in this direction that whether zeta 5 is irrational or zeta 7 is irrational. Explicitly, we do not know. In the same direction, we have a result known as Ramanujan's formula of zeta of 2m plus 1. So he gave this formula. In the first glance, this formula look quite complicated, but if you look closely, what he did, he takes zeta at odd values and have added with the Lambert type of series as the infinite sum. And if we see in the right hand side, we have zeta 2m, this infinite series, and in the right hand side, the only differentiate from left hand side is just we have changed alpha to beta. And outside we have alpha and minus beta to the power m. And still we have in the right hand side one extra term as a finite sum of these Bernoulli numbers. So this function itself, this transformation formula itself contains a lot of information. Like it connects with theory of modular form. It have connection with quasi-modular form. Also, people study this finite sum we have in the right hand side. And here it is defined for all integers except for m is equal to 0, because we cannot take m is equal to 0 here. As it is, it will become I mean, zeta has a residue as 1. Now, let's see what implications we can have for this transformation formula. So, what we do, we'll take alpha is equal to beta. If we take alpha is equal to beta, this left-hand side, the terms inside this curly brackets becomes the same thing that we have in the right-hand side as the curly brackets. Alpha, if we take alpha is equal to beta. Now, the next thing what we'll do, we'll take m as odd integers. If we take odd integers, so this will become minus and we'll be able to add it, and we'll get a result known as Lutz identity. And if you see, if you're taking alpha is equal to beta is equal to pi, and m is equal to 2m as odd, so we have this zeta of 2m plus 1, that zeta at odd, with plus infinite sum Lambert type series equal to something of pi to the power 2m plus 1. And this something we have in 2 to the power 2m and finite sum, they are rationals. As they are rationals because Bernoulli numbers are rational and it is a finite sum, so they are rational. So from this result, what we can say? We can say this zeta of 2m plus this infinite sum is transcendental. So their sum is transcendental. If you are taking this finite sum, I mean not finite sum, if you take for example m is equal to 1, we have zeta 3 plus 2 of this infinite sum. If you know about rationality or irrationality of this infinite sum, we could have more information. So we can say from this above relation, at least one of them should be transcendental, and it is known as a Judelin type result. The next thing, now we'll see what, now we want to see the connection with the modular form. So if we take m is equal to -1 in the Ramanujan's formula at for odd integers, so we'll have this relation. And if we put alpha is equal to I pi z, and alpha is equal to minus pi I z, and beta is equal to I pi upon z, then we'll able to prove this inversion formula, inversion condition for modular relation, that E at even and Einstein series follows this, where Z belongs to upper half plane. Now, similarly, if you want to see the quasi-modular form, if you are taking m is equal to -1 and change alpha by minus pi I z, similarly, beta will have pi I upon z, then we'll have this relation. And if you apply this condition to this relation, then we'll able to get this result. And we have something error term in the right-hand side. Then it is known as a quasi-modular form. Okay. Now we know about zeta functions. I mean, basics of zeta function. It is what is behave as even integers and odd integers. Now we will move to this Koshlikov's manuscript. So Koshlikov, he is a Russian mathematician, and during World War II, he was in jail, and in the jail he wrote two manuscripts. The first one got lost during the transition from jail to mathematical community. But the second one, a study of class of transcendental functions defined by generalized Riemann equations. This is the subject of today's talk. And recently, Dikshit and Gupta have studied the same. Recently, paper is based on this manuscript. Now, before going to what is zeta p function and eta phi function, I mean, what is Koshlikov's zeta functions, let's comes to Hamburger, and he gives some kind of characterization for Riemann zeta functions. So what he says, he proved that if you take two functions, f of s and g of s, where both of them are Dirichlet series and both of them are convergent in the right half plane, sum of the right half plane, but f has a moromorphic function with finitely many poles, and this pair of f and g satisfies this functional equation. So this functional equation is the same functional equation we have for zeta function, just zeta s is changed by f of s, and 1 minus s we have changed by g of 1 minus s. And then he proved that f of s and g of s will be constant multiple of Riemann zeta function. Further, I mean, if you want to see the example for this type of function, we can take any constant multiple of Riemann zeta functions. Those will behave as an example for this theorem. But further, he gave that if we take f in the left-hand side as a Dirichlet series, but we can have in general a non-Dirichlet series in the right-hand side. But now the question is, do we have an example for this type of relation? I mean, we have some pair F and G for which satisfies this relation. Yes, we have actually. It is known as a Hurwitz formula. So what is non-Dirichlet series? Non-Dirichlet series meaning the numerator should be depends on S. And if we see in the Hurwitz formula, this tan function depends on S. So right hand side we have a series, a non-Dirichlet series, but this doesn't consider as a good example because here we have a domain restriction that it is only valid for real part of S is greater than 1. So we want, I mean, this will not work as an example for this relation. So here comes Koslykov zeta function. So Koslykov gave these two pairs of zeta functions. So first, assume P is a variable, P is a parameter. We are taking P tends to P is greater than 0. And lambda 1 and lambda 2 are positive roots of this, increasing positive roots of this equation. And this equation comes from a problem of heat equation. So what he gave? So first he gave zeta P of S as defined as an infinite sum of this. Now, this function in the first looks a bit difficult, complicated. If we see in the numerator, we have a polynomial in P of degree 2. In the denominator as well, we have a polynomial of degree 2. And if we look closely, if you observe that P and lambdas are greater than 0, so numerator is always greater than, denominator is always greater than numerator. So it is always less than 1. It just impose very small value. Similarly, this is a kind of more general of Dirichlet series. He gave a non-Dirichlet series, which he defined as eta P of S. He is defined as infinite sum of this bracket function upon k to the power s. Now, these two functions, zeta P of S and eta P of S, is defined for real part of S is greater than 1, and there also is analytic in the same reason. Now, next, let's see what is this bracket function. So the bracket function is defined in this way. It is defined as a 1 upon gamma function of this integral. Now, what is this nu? I mean, here is a new variable, a variable nu. So nu is always, whenever we mention in the slide, upcoming slides, nu means 2 pi p. Nu is just 2 pi p. Let's see how it behaves as a limiting cases. This bracket function for limiting cases. The limiting cases P tends to infinity and P tends to 0. If you take P tends to infinity, because nu is 2 pi p, so these fractions are the polynomial of the same degree in P. So they will become 1, and the remaining term will become gamma function. So for P tends to infinity, we will have 1. And for P tends to 0, this will become 0. So we'll have minus x upon x. So it will give minus 1 to the power k. If we take outside of this 1 minus k, we'll have P, everything will be cancelled because this integral will become gamma function. So this bracket function will become minus 1 to the power k. So for limiting cases like P tends to infinity, this bracket function is 1. And for P tends to 0, this is minus 1 to the power k. Now let's see, we want to see what is how this roots, we are taking lambda 1, lambda 2, how they are behaving in the limiting cases P tends to 0 and P tends to infinity. Let's see P tends to 0. If we take P tends to 0 in this equation, so the only term is remaining is cos pi lambda. As we are taking positive roots, so only solution to this cos pi lambda is j minus half. Similarly, for taking P tends to infinity, first we'll divide by this equation by P, then takes P tends to infinity. The only term that will survive is sin pi lambda. As we are taking positive roots, so the only solution to this sin pi lambda will be j. And we see if we take P tends to infinity to zeta P function, because zeta P's have some polynomial, same degree of polynomial. So infinity case, they will become 1, and lambda j's behave as j. So they will become Riemann zeta function. And for P tends to infinity, eta P also becomes 1 because this bracket function becomes in this limit case. Similarly, if we take P tends to 0, so for P tends to 0, we have a different root and bracket function is behave as a different. So we have a different value, but that is also entire function multiple of zeta function in the both cases. In eta P case, for we have entire multiple of zeta of S. So Koslykov shows that these two pairs of Dirichlet or non-Dirichlet series are related, and they are related by the same functional equation that zeta P of 1 minus S is defined in this form. Now we know about zeta P functions and definition of zeta P function, how they are related. Now we'll move to what is Euler's formula for zeta P. So Koslykov himself in his manuscript proved that the analog of Euler's formula for zeta P case. So he proved that zeta P of 2m is defined in this form. Here we have Bernoulli numbers that depends on P. And we call it as a Bernoulli number of type 1 or kind 1, or we can say first kind. And these Bernoulli numbers is defined as an infinite integral in this form. Here sigma P function is defined as this infinite sum of this. So this sigma function is defined as a infinite sum of this fractions of polynomial in P e to the power minus lambda j t. If we take P tends to infinity, so see, if we take P tends to infinity, the sigma P will become 1 upon e to the power 2 pi x minus 1. So for P tends to infinity, these Bernoulli numbers behave as a classical Bernoulli number. And here we are taking sigma P function. In the next slide, we have a different sigma function. So in the same paper, Dixit and Gupta have proved the Ramanujan's analog for this zeta P function. And what they did. So for the classical case, we have something zeta of 2m plus 1 here and something Lambert type series here. But here we do not have that same kind of series. But this is also interesting, the series we have. Like if we observe that the only difference, the terms we have in the curly brackets to the right hand side, that if we change alpha by beta, we'll get the same thing, right? Here we change alpha by beta, we'll have right hand side. Here, sigma function is defined in this form, the fraction of single degree polynomial in P. Now, if we take P tends to infinity, this fraction becomes 1, this fraction becomes 1. The sigma functions also, because they are of the same degree polynomial, they becomes 1, and lambda j behave as a j. So for P tends to infinity, we will have and we know that for the P tends to infinity, these Bernoulli numbers also behave as a classical Bernoulli numbers. So for the P tends to infinity, we will have a Ramanujan's formula for Riemann zeta functions, right? Now, they also gave implications for this theorem, but I am not going into that. Next is the question they have asked in their paper. I mean, they explain that we have a closed form evaluation for zeta P2k plus 1 and zeta P at events. But now the question is, they ask that it may be interesting to try to get a closed form evaluation of zeta P at negative odd and zeta P at even, as well as try to get, I mean, if there exists a Ramanujan type formula for eta P at odd, if it exists. I mean, why it looks a bit difficult to do for this non-Dirichlet type series eta P. I mean, it is different because everything we can do for zeta P, it is quite easy than eta P, because zeta P is a kind of Dirichlet series, but eta P is not a Dirichlet series. So doing things for eta P becomes a bit difficult than zeta P. Now we'll try to answer to these questions. So the first will prove the eta P Euler's analog formula for eta P case. So if we apply the functional equation of zeta s to the Euler's formula, then we'll have zeta of minus m of this function, where m is natural number. Now, analog of this for eta P case, we have that zeta P is minus of minus m is equal to this function. And where this Bernoulli numbers, we call it as a Bernoulli numbers of second kind in P setting. And if you apply the functional equation in the same relation, we'll have this eta P of 2m is equal to 1 minus 1 to the power this with the Bernoulli numbers. How we are defining these Bernoulli numbers? This Bernoulli numbers is defined as a infinite sum of this, that is T of sigma Pt. Sigma Pt is an infinite sum involving exponential, minus exponential functions. Okay, so we have an analog for eta P of 2m. Now let's see some examples. Now if we take m is equal to 1 here, what we will have? We will have eta P of 2 is equal to pi square of B2. Similarly, for if we take m is equal to 2, we'll have eta P of 4 of minus pi to the power 4 upon 3. Similarly, for m is equal to 3, we'll have this relation. And if you observe that, to know the algebraic properties of this non-Dirichlet series eta P function, Koenig-Lejeune eta P functions, we have to know the algebraic, whether it be Bernoulli, this second kind Bernoulli function in P settings, rationals or irrational or transcendentals, or for which P it is depending to be a rational. So we do not have the result for this. Okay. Now next comes to the proof of this theorem. So let's see the proof. So what we do, we'll take this generating series. So the idea of the proof, we want something in the right hand side so that we can compare and we'll able to get the result. So what we'll do, we'll take this left hand side, which is equal to this, and now we'll write this inverse Mellin time form relation of this exponential function, which is in this form. Now we'll take this infinite sum to inside this integration. We'll have gamma of s, zeta p of s t to the power minus 1 minus s. Now, what we'll do here, we have a complex integration in the, line integral in the complex plane. Now we'll take C in the right half plane greater than 1, and we'll take a rectangle contour. So one vertical line will be in the left half. For example, we can take the left line in the less than -1 line. And for the positive, that C line, we can take in the right half line greater than C. So what are the poles of this integrand? The first pole we can see from zeta p functions. As I forget to mention, zeta p and eta p also have a pole at s equal to 1. So zeta p has a pole at s equal to 1. So we'll have this form because of this pole at s equal to 1, we'll able to get this residue. And the other sum of residues is coming from this gamma's pole that comes from s equal to 0, -1, -2, and -3 out. Now, because we have a gamma function and it is known that zeta p function is behave as a polynomial growth. So gamma, but in the bounded strip, if we take t tends to infinity, this gamma functions behave as exponential decay. If it is exponential decay and we take t tends to infinity, those horizontal integrals become 0. So only remaining integrals are line integrals, right? So first line integral is become this Bernoulli numbers, and the second will become in the right hand side. So we have something of this Bernoulli terms equal to some finite sum plus this integral. Now what we'll do, we'll take d tends to infinity, and if you take d tends to infinity, this line integral we have in the right hand side, it becomes 0. And if it becomes 0, this is the proof for that it becomes 0. If it becomes 0, we'll have this relation. And if we compare the coefficient of t to the power n, we'll have the relation we have for the, zeta of minus m. And if we have a relation for zeta of minus n, from the functional equation, we can prove that eta p of 2m is equal to this Euler formula. So this is the proof, and this is all about eta p at 2n. Okay. Now we want to see the next result. How this Euler's formula of eta p functions behave as a limiting cases. Okay. So this Bernoulli function of second kind, if you want to write in terms of integration, this is defined in this way: 4m minus 1 to the power m plus 1, integration of this form. This sigma function is defined as a fraction of single degree polynomial, that is p minus x upon p plus x, I think. And if you take p tends to infinity, this becomes 1. And if it becomes 1, this is nothing but a formula. The relation with, it's the same result we have for the Bernoulli number in the classical case. So for p tends to infinity, we'll have this classical Bernoulli numbers. But for p tends to 0, here we have a -1. And if we try to calculate it, we have this result. Now, if we recall, if we take p tends to 0 in the eta p function, we also have the same kind of entire function out of the zeta functions, right? So if we take p tends to 0 in our Euler's formula of eta p, so these functions will cancel out, and for the p tends to 0 and for p tends to infinity, for both cases, we'll get this Euler formula for the classical case. Okay. Now, this is all about for eta p at 2m and their limiting cases. Now, we want to see how do we have this relation for eta p at odd integers. What is the Ramanujan analog for eta p case in the in this eta p setting? Okay. Now we'll shift our focus from odd even to odd. If we observe that for both, for zeta of 2m plus 1 and for zeta p of 2m plus 1, we have a series. For classical case, we have this type of Lambert series. But for zeta p case, for Koslykov zeta p case, we have this type of infinite series. So first we have to get what is this kind of infinite series for eta p case. And we have to develop that theory, for what we will get this infinite series. So to do that, first, let's define exponential p function. So this exponential p function is defined as n is equal to 0 to infinity. And the only difference with the classical function that we have only one extra term, that is bracket function. And if we observe here, this bracket function after some certain point becomes negative, right? For it will becomes negative, it will went to negative half plane. And to get the convergence, we have to first find its analytic continuation. What is the analytic continuation in the entire complex plane? Then we have to find the bound, and using that bound, we'll have this result that this is only absolutely convergent in this region. Okay, now let's see what is the entire. So now we want to see, first thing we want to do that, we will get the analytic continuation of this bracket functions, right? So this If we recall that the bracket function is defined in this manner, 1 upon gamma function plus this into in this infinite integrations. Okay, so this analytic continuation of this is this. If we take s comma nu k, here nu is 2 pi p. If we remember, we have says that nu is 2 pi p. If we take s comma nu k of k, this bracket function, so this can be written in the same reason as this form, right? And here what is u? U is a hypergeometric u function, and from this relation, we can say that this bracket function is analytic continuous to whole complex plane without any singularity. So we can say this function is entire. Now we'll give a very short and outline of the proof. So what we'll do? First, we'll take this nu outside this brackets. So we'll have this first numerator and this is denominator. Now we use binomial theorem and some suitable variable changes in u hypergeometric u function will arrive to this. And here also, if you take z is equal to nu and a is equal to s plus j, c is equal to s plus j minus 1 minus k, we'll prove the first part of this previous theorem. Now, the second part was how this is analytic continuous to the whole complex plane. Why it doesn't have any singularities. So if we rewrite that equation by using this relation that gamma of s plus 1 is equal to s gamma s, we arrive to this relation. So because nu k is greater than 0, always nu is equal to 2 pi p is greater than 0, k starts from k 1. So it has no poles for all s. So the only issue we have this with u functions. And it is well known that this hypergeometric u function is entire except for z is equal to 0. And for our case, it is not 0. So this function is analytic continued to the whole complex plane and have no singularities. Now, next what we'll see. Actually, for the exponential function that we have defined in terms of infinite series, it have a domain restriction. So again, we want some kind of inverse Mellin transformation and analytic continuation of that p exponential function. So this is what is we have. If we can write this infinite series as this integration, here we have bracket function s plus z comma 2 pi pk. And this exponential form or in this form, we can define this exponential to the whole complex plane except for the negative real axis with 0. Now, I will not give the proof of it. The proof is very simple. We'll just take the same contour. We'll have something in the right hand side, a line integral, and the left we'll have a line integral. The horizontal switch tends to 0 as we take t tends to infinity. And if we take t tends to infinity, this integral, right integral will also becomes 0. That's how we can prove it. That's same proof like previous one. Now we want to see the limiting behavior of this function. If we take p tends to infinity of this exponential function, so it will become, because this will become 1, right? So it will become, it is nothing but inverse Mellin transform of e to of minus x, exponential at minus x. If we take p tends to 0, this will behave as minus 1 to the power k, and it will comes outside, and the inside integration will becomes exponential of minus x. Now we are able to, now we can give the define our infinite series that is required for eta p at odd integers. So this is defined how we are defining. If you are taking omega p of x comma m, it is defined as an infinite sum of this exponential function of this upon k of 2m plus 1. So the only difference from previous one that we are changing z by the odd integers, right? Other things are just, okay. Now let's see what is Ramanujan's analog for eta p case. So if you look at here, in the first it looks like what we have. So like similarly, if we see in the curly brackets, what we have is the same thing that we have in the right hand side in the curly brackets, right? Like this, if we change alpha by beta, we'll have right hand side to the left hand side. Similarly, we have a finite sum in the right hand side as well, that involves Bernoulli numbers of second kind. But the only interesting things that we have here, that we have the extra term with odd values, that is 1 upon 1 plus pi p, and it gives very nice results. We'll see in the upcoming slides. Now, if you take p tends to infinity, it will becomes 1, because p tends to infinity, it is 1 upon 1 plus 0. But if we take p tends to 0, it will become 1 upon 1 plus something infinity, right? So it will goes to 0. This for the p tends to 0, this whole term will tends to 0. Right here also we are not taking m is equal to 0 because eta p has a pole at at s equal to 1. Okay, before going to, how it behaves, what is the implications of this? We know how Bernoulli numbers behave at the limiting cases at p tends to infinity and p tends to 0. We know how eta p functions behave as p tends to infinity, p tends to 0. Now we want to see how this infinite sums behave for the p tends to infinity at p tends to 0. So let's take this infinite series first. If we take p tends to infinity to this infinite series, we have this Lambert type series that we have for the classical case Riemann zeta function, that is infinite sum of j to the power minus 2m minus 1 upon of this.
Yashovardhan, can you just show again what's the definition of this capital omega?
Okay, sir.
Oh, okay. This is with your exponential. Okay.
Yes, sir. Okay, sir. Should I continue, sir?
Sure, please.
Okay, sir. Okay, so okay, where I was. Okay, so we have this infinite series. We know all the limiting cases of eta p function, Bernoulli, this Bernoulli function of second kind, and we just want to know how this infinite series behave as a limiting cases. Okay, if we put the definition of omega p and put this p tends to infinity, doing some basic calculation, we'll get this right hand side, which is we have in the classical case of Riemann zeta functions. But if we take p tends to infinity in this case, then we'll have this result. Okay. Now see what is the implications of this Ramanujan's formula. So the first, just take, for the p tends to infinity, we can directly say it becomes Ramanujan's formula, because this infinite series become Lambert type of series, zeta p becomes kind of zeta functions, and Bernoulli numbers also becomes zeta function, classical Bernoulli numbers. So we can say p tends to infinity gives the result for the Riemann zeta case, Riemann zeta functions. Now let's see if we take p tends to 0. If we take p tends to 0, we'll get the result given by transformation from given by BC this Burns formula, and this Burns formula says that we have an infinite series, and we have this infinite sum, and we have something infinite sum. This is become, because we know that if we take p tends to 0 in the Bernoulli numbers, we have the extra terms this, and because of this we will have the extra term this. And where this eta p of 2m that goes, because as we are taking p tends to 0, we have seen, in the previous slide, this eta p of 2m plus 1 with some 1 upon 1 plus pi p will give us 0 for p tends to 0. So for p tends to 0, we'll have this case. Now if we take m is equal to minus n and minus 1, then what we will get? If we take this, similarly, it looks a bit complicated, but see, if we take p tends to 0, here, so this will become 0, this is also becomes 0 for p tends to 0. Only thing will remain this infinite sum, right? So for the p tends to 0, we'll get a very nice, beautiful symmetric result, which we got from, which is given by Cauchy, and this is defined in this form, right? We'll have an infinite series in the left-hand side. We'll also have an infinite series in the right-hand side. Now, what next we'll do? What we'll get from this result? If we take m is equal to even, right? M is equal to 2m and alpha is equal to beta. If we take alpha is equal to beta, this infinite sum is equal to this infinite sum, right? If we take m is equal to 2m, this beta will become minus, this whole series will become minus and we'll add it. But if we take m is equal to even, so it will cancel out and it will become 0. So we are only interested for m is equal to 2m. So if we put m is equal to 2m and alpha is equal to beta is equal to pi, we'll get this result. This is also given by Cauchy. And if we take for the p to infinity case, if you do the same thing, we'll have this result. From both of the results, we can see that this infinite sum is rational, right? It is 0, and this is Bernoulli numbers fraction of some rational number. Okay. Now let's see what will happen is large types of identity. If we take alpha is equal to beta and if we change m by 2m, then what we'll have? We'll have a zeta of 4m plus 1 equal to this. We in the previous slides, we have in the left-hand side this infinite sum. So we'll have the classical case for the Riemann zeta function. If we take p tends to 0, then we'll have a very nice result, which is given by Cauchy. So we'll have this results. If we observe here, we have an infinite series in the left-hand side, but in the right-hand side, we have pi to the power 4m plus 3 into something of rational. How? Because everything inside this series is rational. So we can say this infinite sum that we have is transcendental number, or pi to the power 4m plus 3 multiple of rational. So for p tends to 0, we are getting this result. Now let's move to m is equal to -1 case. If we take m is equal to -1, then and for p tends to infinity, we have to put alpha is equal to beta, we'll have this result. And for p tends to 0, we'll have this result. This is also due to Cauchy. And similarly, if we observe with these two relations, this both of the infinite sum, we have these are transcendental, right? Okay. Now next move to m is equal to 0 case. If we take m is equal to 0 case, so we'll have this result, this transformation formula. And similarly, if we have p tends to infinity, we'll have this result known for classical case. And this results we also get, this is given by Cauchy, this transformation for the p tends to 0. This is also a very nice transformation. Okay, now let's move to the generalized Einstein series. So we define EKP of Z is equal to this. K is positive even integers. Here we have one another assumptions that as we do not know about the specifically zeros of eta p function in the left half plane, so we assume that eta p of 1 minus k is non-zero. Okay. And if we take to p tends to infinity to this Einstein series in p variable, it will reduce to our classical case. Okay. And with the suitable changes for the Ramanujan's formula we have for eta p at odd, like what changes we'll do? We'll take m is equal to minus m, and m should be greater than 1, and put alpha is equal to minus pi I z with some b, and beta is equal to pi I upon z. We'll able to prove this condition that we have inversion condition for this modular form. But because this ek function is not periodic, I mean, ek of z plus 1 is not ek of z, so these are not modular forms. How we can, and for p tends to infinity, we'll have the classical Einstein series. Okay. Now for the Cauchy modular form condition, if we put m is equal to -1 and do the same kind of suitable changes in the Ramanujan's formula for eta p at odds, we have this relation. We have this relation. Okay. Here we have in the right hand side this error term, and if we take p tends to infinity, we'll have this result from his directly. Okay. Now let's see the proof for the Ramanujan's formula for eta p at odd case. Let's take the infinite sum that we have in the formula. Now what we'll do, we'll write the definition of omega p as this exponential function. Now we'll write this exponential function that we gave in analytic continuation in terms of line integration. Okay. After now we are proving for positive integers now, and similarly we can do the proof for the negative integers. So here m is positive. So here we can take s is greater than 1. Okay, so we are changing exponential p function to this function and taking this infinite series to inside. We'll have this eta p of, and doing some suitable changes, we'll arrive to this integration. Okay. Now what we'll do? We again take a rectangle contour in the complex plane. So the C line that we will take, it is in the right half plane greater than 1 line, and the D1 line that we have horizontal line that will in between of 2m plus 1 and 2m plus 2. Okay. So as this r minus 2 is coming, okay, so we have a pole. One pole is as s is equal to 0 because of eta p of 1 minus s, and another pole because of eta p of s plus 2m plus 1. So if we put s is for this, I mean, for r is equal to 0, we are getting, I mean, or not, we are getting the residue because of eta p of 1 minus s. Similarly, because second eta function, we are getting this pole, and all other these residues coming from this cos function. Now we have a 2 horizontal line, 2 vertical line, like previously we we take, oh, here one typo, here it will be t. Okay. So now what we'll do, we'll take t tends to infinity. If we take t tends to infinity and cos function have a exponential decay, 2 exponential of minus pi of mod t by 2, and this eta p function also have this polynomial growth. So we'll just only remaining with the left hand, this right hand integral, and the right hand vertical integral and left hand vertical integral. We know the series representation of right hand integral, but we do not know the series representation of representation for left hand negative of integral. So what we do now? So we take this suitable changes s2 minus s minus 2, And after doing suitable changes, this integrand C will become in the right half plane. And comparing with the coefficient, comparing with the infinite series that we have in the previously, we'll have this result with the suitable changes. The change will do, they will choose x is equal to 2 alpha, and we'll also multiply by alpha to the power minus m in the both hand side, and we'll use this Euler's formula for eta p function. So after putting all these things, we'll able to get the result for the eta p at odd integers. This is all about eta p at odd and even that we have. Now we have seen, now next we'll move to one more interesting thing that we know as the Ramanujan polynomial, that we have a finite sum in the right hand side of the Ramanujan function, Ramanujan formula for odd integers. So Jagier have studied this rational function pk of z as this, and we can get this function from Ramanujan's formula itself. So in the right hand side that we have finite sum. If we change alpha is equal to minus pi iz and beta is equal to I pi iz, I pi by z, and changing this and re-indexing that summation, then we'll able to come to this relation. Okay. Jagier give two very nice functional equation to these rational functions. First, he shows that this satisfies two-term functional equation. So this two-term functional equation pk of z and this is equal to 0. Then he also proved the three-term functional equation that pk of z minus pk of z minus 1 plus something of this is equal to 0. So one more thing that is a point of study to the mathematicians, that these author have considered this z of pkz as a polynomial and called it as a Ramanujan polynomial, and studies their zeros and behavior in the complex plane. Okay. Now we are also willing to study this relation of what kind of functional equation we could have for our p settings. So we are taking this pk of this function as this a finite sum, this rational function, as we have for the classical Bernoulli numbers. Here L1 means we are taking the Bernoulli numbers of first kind, that is Bernoulli numbers for zeta pk's. And for L is equal to 2, we are meaning that Bernoulli numbers of second kind that we have for eta pk's. Okay. So we tried and we are able to get these some results. So if we take for two terms functional equation for L is equal to 1 and 2, for both these two-term functional equation will satisfy. And if we take if you think about three-term functional equation, so three-term functional equation will not be exactly 0, but it will give us some error term. What is that error term? If we take for L is equal to 1, so we'll have this error term, and more precisely, we are saying the 2 to the power 2k coefficient of this function. And this function, the denominator is depending on p. And if we take p tends to infinity of this function, it will become 0. So for p tends to infinity, this error term becomes 0. Similarly, for e of 2, that is we have Bernoulli numbers of second type, we are taking this function t to the power 2k coefficient of this. So if we take p tends to infinity, in the same case, this is also will become 0. Okay, this is for now. We have some question that we want to know. The first thing, are the p Bernoulli numbers are rational? Whether it depends on p, that is like it is depending like pi p is rational, then it is rational, or something condition comes with p, and what is that condition? Second question, do we have a theory like we have for the classical Bernoulli numbers, like recurrence relations and other things that we have for Bernoulli numbers? Do we have it? And the third is that, like we have a very nice relation, functional functional relation with the eta p. We have a zeta p in the zeta p of 1 minus in the right hand side, and eta p of zeta p in the left hand side, and eta p in the right hand side. Similarly, do we have this kind of relation for our two Bernoulli numbers? The third one, like in the classical case, there is some gamma function for exponential classical exponential function. Do we have a p gamma function or something like that for this p setting of exponential function? And what could be other properties of this p exponential function, like we have for classical Bernoulli number, classical exponential function? This is all from my side. Thank you so much.
Thank you, Yashovardhan, for the nice talk. Any questions?
Vishal had a question in the chat, so maybe he can ask now.
Yeah.
Vishal.
Yeah, no, I think the answer was already given in the last slide, which is, yeah, so my question was if these P Bernoulli numbers are rational functions in P. I
So
think,
yeah, we do not know. We tried. We have some infinite kind of series, but I mean,
mhm,
we cannot say. We do not know.
I see. So, but have you computed like the first few P Bernoulli numbers, for example?
We tried, but actually we do not get a good. I mean, we do not get a perfect relation. So I do not have.
I
No,
see.
Yeah.
I mean,
Like, do you,
yeah, sir. Yeah,
Yes.
please, Vishal.
no, no, I was just wondering if you like if you have put this on a computer and tried computing the first few terms, first few numbers, and then or maybe for certain specific values of p, like maybe take
Yeah.
p to be powers of 10.
For specific values of p, we do not compute it.
Uh-huh.
But for general p, we do not get result. I mean, for specific values.
Oh, you mean if I want to know B2, 2 comma P, that also is not possible to be explicitly computed?
Yeah. In terms of integral, we have, but like specific values, we do not have.
Okay.
But no, but inside the integral you have this function sigma,
Yeah.
right?
Yes.
And you're saying that it's still not possible to explicitly, like
Uh,
Mathematica cannot compute this for.
okay. I think uh, I tried, but did not get some good results. I do not remember actually.
I see.
I
Okay,
tried actually,
okay.
but do not have some
But
concrete results. That's why.
but what? But what's the belief? Do you believe that maybe
Yeah,
these
I
are
believe
rational?
that much. I believe that it will depend on P, and I think if pi P is rational, then it will be a rational. I think the result
Okay,
will come in that manner. That is my intuition.
okay, okay. Thank you.
Yeah,
So
like it. Yeah, yes, sir. Yes, sir.
sorry, yeah, please go ahead.
Like it will come my maybe some polynomial kind of relation with 1 plus pi P in Bernoulli numbers. I mean, I do think it will come in that way. Yes, sir.
Yeah, when you started your first proof, I think it was for B, uh, the first proof in your talk.
First proof for it. This.
No, for the Bernoulli numbers in terms of the zeta function at 1 minus n.
Okay. Okay. Yes, sir. This proof.
Yeah, just before that, when you had that generating function for, yeah, this. Here also, oh, here you get t between 0 and 1 only,
Yes, 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 sir.
not 2 pi or
Yeah,
2.
yeah, sir. We can because this series is actually this series is divergent for t is less than 0. We need something analytic continuation of this infinite sum to go in the left half plane. I mean, we can put here mod t here, but
Okay,
yeah, but it will be in between of 0 and 1. It should be 0 and 1.
okay. So mod t less than 1.
No, sir. I
No,
mean, no.
no.
In the negative half plane, it is not. It is just for positives in between 0 and 1. I mean, in between 0 line and positive 1 line.
Okay.
Yeah.
Okay, thank you. Yeah. Any other questions?
So yes, like in the case of Riemann zeta function, like we have this trivial zeros. So do you have some trivial zeros of Koslykov zeta functions as
Yes,
well?
sir. Yes, sir. Eta p and zeta p both are zeros and negative integers. Similarly,
Okay.
both of the Bernoulli numbers are also zeros and I mean, from here we can see if we put m is equal to evens, so here the odd Bernoulli numbers will be 0. So for
Okay.
both the kind of Bernoulli numbers, at the odd we will have 0.
Okay.
And the both functions also shares the same trivial
So
zeros.
there, like P can be anything still.
Yeah, yeah, they are
It
0.
is.
For p is
Okay.
for p anything. For general
Okay.
p we have.
Okay. I see. Okay. Thank you.
Yes, sir. Thank you, sir.
Any further questions? If not, let's thank Yashovardhan.
Thank you, sir.